Dobar dan svima, dobrodošli na sesiju Rashladne mašine i sistemi. Hello everyone, welcome to the session about refrigeration system and machines. So for today we have about 5 different presentations, different papers. So we will begin. I will ask the presenters of the papers to keep the 50 minutes of their presentation, and after that we will start with a short discussion. I encourage the audience to ask questions because there are different interesting topics here. So if there's no question now, I can now start with first presentation. First presentation is prediction of cooling energy consumption using machine learning models. The presenter will be Professor Aleksandar Sitenović-Dobrić from Faculty of Mechanical Engineering, University of Belgrade. So, Aleksandra, floor is yours.
So, hello everyone. Today's topics are prediction of cooling energy consumption using machine learning models. As a short introduction, we are all aware of the increasing need for cooling. So definitely building sector actually is responsible for 30% of global final energy use and nearly 26% of greenhouse gas emissions according to the International Energy Agency. If we look at the numbers in Europe only, heating and cooling represent nearly half of total final energy demand. Of course, dominantly this consumption comes from heating needs, but if we consider that buildings are now more and more isolated, these percentages are starting to change, even though the current state of the cooling energy consumption is that nearly 3% or 7% depending if the building is residential or commercial, we spend on cooling. But it is expected due to the cooling energy use that the total heating and cooling energy use will increase by 67% until 2050 and nearly by 170% by 2100, relatively comparing to the levels that we have in 2010. This is mainly due to the cooling consumption, so definitely this ratio will change and cooling consumption of buildings is significantly increasing. There are several reasons for that. Raise of GDP, raise of people expectation about comfort, raise of number of people, raise of the buildings, commercial buildings that we use, and therefore the needs are significantly increasing. So the energy efficiency of cooling system is in focus in the last period. So that's why the accurate prediction of cooling energy consumption is crucial. I love the sentence from energy managers that you cannot improve. You cannot improve what you cannot measure. So first, if you want to improve energy efficiency, you need to have the accurate knowledge about the cooling energy use. So this actually paper is a continuation of research done in Korea, where our colleagues worked on a building where they developed a cooling energy use prediction model, integrated it in BMS system, and use this AE-driven control for cooling system. They have evaluated that this kind of control leads to significant energy savings. So our further step is to develop more accurate models. So it is expected that more accurate model could lead to more energy savings. So these kind of models have a significant practical application. And it is expected that this application will be even more important in future. You all know that currently many systems are AE-driven, so especially systems that have large energy consumption, these systems are very in focus for further energy savings. So we presented three different models. All are decision tree based. All of these models are decision tree based. So I will not bother you a lot with the models itself. I will just shortly present the three of them. First is decision tree model. Actually, machine learning is very important for these kind of predictions because these like black box models, because you don't know actually exactly what is happening when this model are predicting cooling energy use, but they are very accurate in predicting. Among them, decision tree is one of the interesting models because it has like a tree-like structure and are very computationally are very efficient and well suited for handling this kind of data. They're especially useful when you have a lot of missing data because they are robust to outliers and missing data, which is very important for these kind of predictions. However, they are prone to generating very deep and highly specialized trees. That's why they have actually tendency to overfit. One of the ideas to improve the accuracy of these models is by creating ensemble. So random forest is a representative of bagging approach of ensemble techniques. So random forest model, practically it is ensemble that is constructed out of a larger number of randomized decision trees. And gradient boosting machine is the third model, which applies boosting methodology. In random forest model, all trees are trained in parallel, while in gradient boosting machines, they learn sequentially. Like the decision tree is practically developed based on the errors made of its predecessors. Let's go to the part which is more applicable. So the case study was a 10-story office building. It has over 40,000 square meters. We basically did not change the input variables used, which colleagues from Korea used for their modeling. So this is very simplified schematic of HVAC system in these buildings. Basically, they have both turbo chillers and absorption chillers, but during the measurement period, only turbo chiller and one cooling tower was in operation. So all the measured data refer only to those two parts of the equipment. So they have 11 measured input variables and one output variable, which was the total cooling consumption of building. Altogether, the electricity consumption of the chiller, of the pumps, and also of the cooling towers. So the interesting thing that this case study, this data set is based on the real world measured data set. So here are the results. Of course, there are more than 1,000 data points used in this study. So we split, which is typically, we split the data into the training and test data set. So all models are trained and evaluated on the training data set, and then we give the model the test data set, which is completely unseen by all of the developed models. So we can see how well our model can predict, how accurate it can predict cooling consumption. So basically, always the test period is the one which is more important to us. So we can see that the ensemble approach achieves better prediction accuracy than the single individual model. These results are also better than the results that achieved our colleagues in Korea. That's why further steps, that's why also our further research goes to improving the presented models so they have less error in prediction, which we expect will lead to more significant energy savings when implemented into the AI-based control. So we can see we have some prediction metrics which are typical for this kind of research, coefficient of determination and the different types of errors, but we can see that random forest achieves best prediction results, which is better than any of the single decision trees or gradient boosting machines. So here we can see the comparison of the regression plots and error histogram for each of the models. So we can see the decision tree that is due to the top of the model has predictions that are closely the same average value, never mind the measured cooling consumption. But the error histogram shows that the majority of the errors are in a very narrow sector, all around zero. and has nearly normal Gauss distribution, which means that all models are very accurate in the prediction of accuracy. Here we have the comparison of the measured cooling consumption and the prediction of different models. So to conclude, you all know the cooling energy consumption is very hard to calculate, and that means that it's even harder to predict because of the strong non-linear and codependent relationships between variables. That's why the previously developed white box models or just solving the equations is not efficient enough in prediction of cooling energy use. That's why the black box models, especially machine learning and artificial intelligence, are the future of prediction of this kind of energy use. So in this case, we achieved best results with the random forest model. And the most important, the applicability of this model is very high because it can be integrated into BMS. So the system operates by calculating the minimal, so it predicts actually the cooling energy use, finds the minimal, finds the input variables that will give you the minimal cooling consumption, and they can use it for further control of the cooling system. So the future research will be, the topic of the future research is to improve even more the prediction model by using some other ensemble methodology or applying meta-heuristic to optimize the parameters of each individual model, etc. So that would be all from me today. If you have any questions, you can do it now or at the end of the session.
Thank you, Professor, for an interesting presentation. Is there any question for Professor? Okay, if there is not, we can proceed with the next presentation. So the next presentation will be from Marco Ferron, from Carel. It's a sustainable future with a total storage. So, Marco, the floor is yours.
Thank you to everyone also for the opportunity to present this study that we made in collaboration with one big retailer in Romania. As you can see, I am not from the university. I am from a private company that is Carel. Carel is a producer, an historical producer and designer of solution for the HVAC and R, so for air conditioning, but also for food retail and refrigeration, with a focus mainly on the three pillar, the electronic part of the mechanical, and in this moment also for the data processing. So everything what is BMS, SCADA, or solution like that. So. As you can imagine, as Carel, we are really focused like other company and like we were, you saw before, to develop a solution with the high possible level of efficiency. So, and in a theoretical world, everything is really beautiful. So the idea is that everyone will start to use the most advanced solution, the most a solution with the highest efficiency, and could be that in the future will be like that. But if we go in a pragmatic way, if we go, for example, in food retail, in this moment the retailer already have the shop. So one point is to ask them to reduce the energy consumption and to reduce their footprint. Another point is to force them to change everything for new system. Why they need to do? They already investing for that. Was one of the questions that we had in mind when we started the project, this kind of project. What I'm going to present is a project that is based on a large volume of data. We are speaking about 1,000 stores only in Romania, so it's not one. It's something that is realistic and already done, and with years of data and millions of data. And we started from the challenge that in the commercial refrigeration we understood from the different players. So for sure, everyone wants to find a way sooner or later to follow the new rules. In Romania, they already go to CO2 system. They want to install all the new system with the highest efficiency. But the other challenge they have is that, okay, in the store that we already did, that are the majority, because if we speak about a retailer with 1,000 stores, probably in the next 2 years they will do 100 stores, but they already have in operation 1,000 stores. How to drive and reduce the complexity and how to have a real impact on that. So we started to speak about it, to combining few points. So the efficiency, not only for the single machine, but for the system itself. Connected also to the fact that, okay, we have in this moment the possibility to connect with the IoT and to collect a large number of data. So the point was to understand how to drive the data and have a result from this data. So finally, what we did, so we sit down with the retailer, understanding the needs they have, and with the solution that, okay, in this case, a solution made by us, so because we are a private company, but we understood together how to integrate in a complete system everything they have in all the store. I mean, try to imagine you are in front of one retailer and they have 1,000 stores, it's not one, and if you go in one store, you can understand the complexity is huge. So we are not speaking all about refrigeration. We are speaking about refrigeration, lighting, air conditioning, everything, including the small fridge for the Pepsi Cola that they have. So how to give them a realistic impact on the actual energy that they are consuming. Because it's true that if they find a way to reduce 1, 2, 3, 4% of the total energy consumption, the impact on the total network will be huge, and that's the point. So, finally, in a project that took around 4 years, and imagine that we work in a medium of 350 shops per year with 30 different companies involved, not only the retailer. For each shop, we found a way to connect to a BMS system all the possible consumption points. So from the lighting, imagine the lighting from the parking, to the HVAC, refrigeration, all the devices that are included. Doesn't matter if our device is produced by Carel or not. So we find a way to integrate, collect all the data, then you have a huge number of data, and find a way to drive the data in order to give an automatic result. So to automatize a lot of operation and reduce the human factor in the shop. And finally, we connect all the 1,000 shops in one remote system to give to the management the possibility to drive even strategic decision, because, okay, the system can give a huge benefit, but part of the benefit is also from the manager that need to understand the data. So, and why they need to understand data? Because with the data they have in their hand, they can drive strategic decision and took some decision that can have an impact. And the impact, finally, for them will be saving money. So that's the point. They are working for that. But in reality, it's also a CO2 reduction, a huge CO2 reduction that we had. So the study, as I told you, is a real case study, one of the largest that is possible to have in this moment on the market. So it's based on a Romania retail chain that is Mega Image, part of the lease group. The solution that we applied was necessary for us to find a name, and we call like Total Store, because we are controlling the total solution inside each store, and was designed to drive 4 targets of the retailer, for sure, but there was a reduction of carbon footprint, OPEX, optimization, was a key point. Food quality improvement, that is, as a result, you will have a reduction of footprint, and monitoring of all the data and all the information, and give the data in the right way. As we spoke, we were connecting for all the existing stores. When we started the project, was around 800 stores already on operation. Everything was available, from HVAC to the last split that is in the shop. For the new shop, the retailer decided to do a step more. They was working in order to implement 100% CO2 solution with the reverter driven, so to benefit also from additional saving from the system, and in each one to have the right BMS local and remote. After the job, the picture was amazing, because only looking from the system was possible to see, as we spoke, 1,000 stores. In this moment are 973 stores that are connecting to the same system. And imagine that everything from the retailer can be managed from a central part by 2 persons. So that can be coordinated by 2 managers, not 200 managers. We focus on some important KPI. One of the first that they gave to us was the HACCP, that was fundamental, and all the energy consumption and all the service performance, because also from service point of view, they understood that if they improve the service level, imagine that they reduce the number of alarm in the store, in the percent that was 90%. So before and after, the result was 90% less alarm in each store. It means less person that are going in the store, less person that are driving. So everything was calculated in a CO2. And then give the possibility to make a comparative analysis between 1,000 stores, not between 2 stores. So that's the point that we did. The result we obtained was that, so the numbers are real, confirmed by the retailer. Last year in Romania, this project received the prize like the best sustainable project from the government of Romania, so the best sustainable project in Romania. We are saving in this moment, the study was done on a number of 576 stores, so not the total volume, but anyhow, you can imagine that is a quite large number of stores and quite a large number of data that can confirm the result. The saving they had in kilotons of CO2 per year, only on 500 stores, was 6 kilotons per year. So imagine that is like that we are stopping 6,600 persons that are flying from here, from London to New York. So that is the impact in CO2. But from the retailer, the main impact was on the saving they had. So the saving they had, calculated on 500 stores, so multiply per 2 because the stores are 1,000. In this moment, it is 5.3 million per year. So it means that they are saving more than 10 million euros per year. So and that's the point. With the return on the investment for them, that was 1 year and a half. So that was the return of the investment. This project was involved with also many technical team on the site, and this helped us also to open some other projects. So other retailers are in this moment looking for similar solution, do the result. And it's something that in this moment, due to the large number of data that we obtain, we are working to implement some solution in order to make an automatic additional optimization using the AI on our system. That's the point. If you want to read the complete story, you need only to scan, and you can find also on our website.
Thank you, Marco, for your presentation. Is there any question from the audience or chairman? Okay, thank you again. Please. So, the third presentation for today is the retention quality and antioxidant capacity of the berry fruits by freezing by Professor Snežana Stevanović from Agricultural Faculty in Belgrade.
Znači, tema je očuvanje kvalitete i oksidativnosti pri smrzavanju jagodastog voća. Tim autora vidite, i ono što želim odmah da kažem da ovo istraživanje je podržano od strane Ministarstva za nauku, s obzirom da je jagodasto voće za nas jako važno i strateški i ekonomski, jeli? Zato je bio deo ovog istraživanja. Inače, smrzavanje ima veliku primjenu u prehrambenoj industriji, naročito kada je cilj dugo čuvanje hrane, odnosno čuvanje hrane u dužem vremenskom periodu. Uz to smrzavanje, posebno želim odmah da nagovestim da sa tim načinom konzervisanja u značajnoj meri se očuvaju karakteristike prehrambenih proizvoda, pa i nutritivna svojstva. Jagodasto voće karakteriše veoma atraktivna senzorna svojstva i to voće je vrlo popularno kod potrošača, uz to veliki ekonomski značaj. Ima uz to specifičan i bogat hemijski sastav i novija istraživanja su pokazala da taj specifičan hemijski sastav upravo ima povoljan uticaj na zdravlje ljudi. Jagodasto voće karakteriše visok sadržaj bioaktivnih jedinjenja i prirodnih antioksidanata i zato je danas to tema koju saopštavam. Inače, jagodastom voću pripisuje se antiviralno, antiinflamatorno i antikancerogeno dejstvo. Novije istraživanja su sve to potvrdila i to istraživanje i in vivo i in vitro, tako da se danas pouzdano može tvrditi da konzumiranje jagodastog voća prevenira neke hronične bolesti, a isto tako i degenerativne bolesti. Zato je cilj ovom istraživanju bio očuvanje kvaliteta, ali i antioksidativnosti pri smrzavanju jagodastog voća, tako da analiziran je uticaj na karakteristike kvaliteta, najznačajnije pre svega fizičko-hemijske, ali i utvrđivan je antioksidativni kapacitet ovih plodova, znači jagode, maline i kupine, te tri vrste Smrzavanje je realizovano u industrijskim uslovima, diskontinualno u komori pri temperaturi vazduha od minus 30 stepeni Celzijusa do postizanja minus 18 u termalnom centru plodova. Kasnije su plodovi čuvani na temperaturi od minus 20 stepeni Celzijusa. Nakon odmrzavanja analizirana su fizičko-hemijska svojstva i svežih, a i plodova nakon zamrzavanja. Zatim, računskim putem je utvrđivan indeks kvaliteta, određivan je i sadržaj vitamina C zbog njegovog značaja, uz to i korelacije sa samim antioksidativnim kapacitetom, koji je takođe utvrđena i to DPPH metodom, koja je jedna od prihvaćenih relevantnih metoda za utvrđivanje antioksidativnog kapaciteta. Možda ovako, znači u tabeli su date vrednosti sadržaja suve materija i udeo vlage, odnosno vode, koji je jako važan kada se hrana konzerviše na niskim temperaturama, zato što upravo voda kristališe i moguće čitava paleta promena. Zbog toga a uz to odmah, znači, možemo da primetimo da jagodasto voće ima vrlo visok sadržaj vode. Jagoda, na primer, čak i preko 90%, što može da se vidi ovde i tako visok sadržaj vode koja kristališe pri smrzavanju, srazmerno tome, srazmerno sadržaju vode stvara se i veća količina leda u tkivu. Pored svog značaja vode, veliki značaj ima suva materija, odnosno sve ono što se nalazi u plodu, a nije voda, tako da je utvrđivan i sadržaj ukupnih šećera. Vidimo da je kupina značajno veći sadržaj ima šećera u odnosu na malinu i jagodu i statistički značajna razlika je utvrđena u sadržaju. Ta komponenta je jako važna i za dalju preradu ovih plodova i smatra se to jednim od vrlo značajnih parametara kvaliteta. Međutim, samim smrzavanjem nije došlo do statistički značajne promene u sadržaju šećera. Zanimljiv je fenomen da kod zamrznuti plodovi kupine nakon odmrzavanja i naravno ekstrakcije za potrebe analize pokazali što nešto veći sadržaj šećera i to može da se tumači time da je lakša ekstrakcija nakon zamrzavanja i odmrzavanja tkiva. I zbog toga rastvorljivi šećeri su lakše mogli da se ekstrahuju i pokazali su višu vrednost. Znači, ta osobenost utvrđena je kod kupine koja je inače imala i najveći sadržaj šećera. Zatim, sadržaj kiselina, maline tu prednjače, u sadržaju u odnosu na jagodu i kupinu, a takođe nije utvrđena statistički značajna razlika u sadržaju pre i posle zamrzavanja. Inače, sadržaj kiseline je jako važan jer je on taj koji daje taj svež voćni karakterističan ukus, tako da je jako važno da se samim smrzavanjem i sadržaj kiseline očuva. Zatim, računskim putem je utvrđivan indeks kvaliteta, QI. On je pokazatelj, odnosno indikator je ukupne opšte prihvatljivosti voća i utvrđeno je da je najveći indeks kvaliteta kod plodova jagode, a najniži kod plodova maline, koje su ujedno imali najveći sadržaj kiselina. Tako da taj odnos, međutim, malinama može da se pripiše upravo taj sveži, osvežavajući ukus. Ali nije utvrđena statistički značajna razlika kod plodova pre i posle procesa zamrzavanja, kada je u pitanju indeks kvaliteta i to je takođe značajan pokazatelj. Osim antioksidativnog kapaciteta, utvrđivan je i sadržaj vitamina C. On je veoma značajan sastojak jer čini voće fiziološki veoma vrednim. Funkcija vitamina C je u organizmu i specifična i neophodna. Tako da zadatak svakog tehnološkog procesa je da ga sačuva u što je moguće većoj meri. Plodovi i jagode imaju najveći sadržaj vitamina C, zatim malina, onda kupina i tu je utvrđena statistički značajna razlika kada su u pitanju ove 3 vrste jagodastog voća. Međutim, nije utvrđena statistički značajna razlika kada su u pitanju plodovi pre i posle procesa smrzavanja. Znači, samo smrzavanje ne izaziva gubitak vitamina C. Rezultati antioksidativnog kapaciteta dati su preko EC50 vrednosti, međutim, izražava se preko količine DPPH reagensa koja je potrebna da bi inhibirala 50% prisutnih antioksidanata. Zbog toga, znači, što je manja EC50 vrednost, to je veći antioksidativni potencijal. I u literaturi često se stvara zabuna, zbog toga smo rezultate izrazili kao vrednost 1 sa EC50, da bi zaista veća vrednost označavala veći antioksidativni potencijal. Plodovi kupine pokazali su najveći antioksidativni potencijal, značajno veći u odnosu na jagodu i malinu. Međutim, zanimljiv je fenomen da kod plodova maline i kupine nakon procesa smrzavanja takođe je utvrđen veći antioksidativni potencijal. To se objašnjava upravo što sam proces smrzavanja nakon odmrzavanja ćelijski zidovi i lamele, takođe i makromolekuli koji se u njima nalaze popuštaju, tako da je lakša ekstrakcija fenolnih komponenti koji čine okosnicu antioksidativnog potencijala, tako da je u uzorcima nakon odmrzavanja utvrđena nešto veća antioksidativna aktivnost. Na osnovu izvršenih ispitivanja i prikazanih rezultata može se izvesti zaključak da proces smrzavanja predstavlja vrlo podesan način za konzervisanje osetljivih plodova jagodastog voća. Analize su pokazale da ne dolazi do značajnih promena fizičko-hemijskih parametara kvaliteta, a nakon smrzavanja u industrijskim uslovima i to se potvrdilo kod sve 3 analizirane vrste voća. Gubitak u sadržaju termolabilnog vitamina C nije statistički značajan, što predstavlja vrlo važan parametar očuvanja kvaliteta. Uz to, utvrđeni antioksidativni kapacitet plodova maline i kupine bio je veći nakon procesa smrzavanja. To bi bili glavni zaključci. Hvala.
Thank you, Professor. Is there any questions now for this presentation from the audience? Okay, thank you very much. Okay.
Samom procesu liofilizacije prethodi smrzavanje. Tako da nam je jako značajno bilo upravo da jako dobro ispitamo uticaj smrzavanja, znate. Tako, liofilizacija se potencira i zaista jeste jedan superiorni način konzervisanja hrane, naročito ovakve, jer treba očuvati i senzorne karakteristike, a to liofilizacija zaista u velikoj meri očuva. Tako da je važno da samim smrzavanjem ne narušimo, pre svega mislim nutrijente, tako da kasnije čak i onim sušenjem pod vakuumom što ide nakon samog smrzavanja, da se ne izgubi. Znači, smrzavanje je deo procesa liofilizacije, tako da možemo da pristupimo liofilizaciji. Zaista, kod jagodastog voća dobijaju se dobre rezultati. Imam iskustva sa tim. Čak sam u doktoratu, jedna od metoda je bila upravo liofilizacija, koja mi je služila kao reper metoda, kao najkvalitetnija i najpouzdanija metoda za očuvanje kvaliteta. Kad ste me već pitali, problem ovde nismo ispitivali nakon dugog vremena čuvanja jagodastog voća u zamrznutom stanju, nego cilj nam je bio sama kristalizacija i sam proces smrzavanja, u kom stepenu utiče pre svega na antioksidativnost i glavne fizičko-hemijske parametre. Znamo da ipak dužim čuvanjem u zamrznutom stanju ipak dolazi do promena, ali ovo nam je bilo samo značajno i zaista možemo da favorizujemo i istaknemo samo smrzavanje kao način konzervisanja. A što se tiče sušenja, s obzirom da je to bilo deo pitanja, tu već dolazi do značajnijih promena i senzornih, a nažalost i nutritivnih, jer samim tim odvijaju se na visokim temperaturama i ovde sam naglasila vitamin C kao termolabilnu komponentu, tako da dolazi i do još nekih promena, ali pre svega kod sušenja dolazi do senzornih promena. I često to tržište ne podržava i ne žele jagodasto voće onako klasično sušeno. Nadam se da sam odgovorila, ako nisam tu. Da.
Hvala na vašem pitanju. Thank you for your question. Is there... Okay, thank you.
Koliko sam ja shvatio, vi ste napravili eksperiment sa šažnjim zamrzavanjem.
Tako je.
Uglavnom u industrijskim pogonima se to radi kontinualno. Da li mislite da bi u industrijskim uslovima ti rezultati bili bolji zbog kontinualnog zamrzavanja?
Prošle godine na kongresu saopštila sam rezultate gde je bilo poređenje upravo tada dva načina smrzavanja. Više ne zauzimam vreme. Nije statistički značajna razlika u nutritivnim, znači fizičko-hemijskim i nutritivnim relevantnim parametrima. Eventualna razlika se primećuje u senzornim karakteristikama plodova. Tip kristalizacije znači pre svega menja senzorne karakteristike. Kod kupine je to osobeno što se menja boja, ali na uštrb kontinualnog načina smrzavanja. Bolje rezultati se dobiju u šaržnom tunelu za smrzavanje. Kod kupine, naglašavam. Da, da.
Da li ste nešto radili na temu kvaliteta kod održavanja? Recimo za mesec dana, dva, šta se dešava u zavisnosti od menjanja temperature? Kako se menja temperatura pogori, dolazi do kristalizacije para. Ja nisam tehnički mašinac, ali sad shvaćam zbog toga kako može da nešto o tome.
Rekristalizacija je nešto što mi tehnolozi se trudimo svakako da sprečimo da do nje dođe. Zato što ona opet ima pre svega utice na senzorne karakteristike. Kako izgled jako često prodaje hranu, pre svega izgled, onda je jako važno da do nje ne dođe. Imamo iskustva sa tim i upravo pri variranju temperature dolazi do rekristalizacije. U nutritivnom smislu menja se sadržaj vode donekle, tako da se to odražava i na druge donekle parametre, ali ono što se postavlja kao imperativ da se spreči da u toku čuvanja da dođe do variranja temperature, jer upravo rekristalizacija predstavlja neprijatelj kvaliteta. Hvala vam.
Hvala vam najviše na pitanjima. So, the next presentation is from Mina Mirović, Altera, review of gray box models for modeling and optimization of HVAC and R systems. So, Mina, floor is yours.
Thank you for this introduction. As Professor said, this is a review paper that my colleague Daniela Srećković and I have conducted for our PhD studies under mentorship and supervision of our PhD professor Aleksandra Sretenović-Dobrić. Before we dive into gray box modeling, I will just give a brief introduction. Why is it important? As you all know, here, the main goals of HVAC and R systems are ensuring thermal comfort, keeping indoor temperature at some level, and also reliable cooling and heating performance. And in order to do so, buildings and these systems require a lot of energy. According to statistics, almost 40% of total global energy is actually used in energy systems. And for that, and having in mind that in recent years, the trend is to reduce energy consumption, researchers in this area have been focused on developing different methods for prediction of energy consumption in buildings. One of these methods is actually gray box modeling. What is gray box modeling? Gray box modeling has been born from two types of models. One is white box, the other is black box. What is white box modeling? White box modeling is a modeling where all information on the systems are known, input, output, and internal dynamics. Those are the models that are based on heat transfer equations, thermodynamic laws, and similar, and they are really precise and accurate, but they require a lot of time and a lot of computational efficiency. While on the other hand, we have black box models. In black box models, we know input and output, but internal dynamic of the system is not known, which is a problem for precise results. Black box models often use regression, optimization, and neural networks for finding that internal dynamics in the system. And idea is to develop gray box model and to combine the best of both worlds in the way gray box models are partly based on equations and partly on statistic and experimental data. And here is a short schematic of the process, how the gray box modeling is developed. First, we need to conduct a model. Afterwards, we assign physical parameters, put experimental data, and test the model itself. If the model has passed the test, by that I mean if the model results from a model are good in a comparison with experimental results, we can form stochastic model. If not, then we need to refine the gray model. One of the most common categorization of gray box model is by serial or parallel approach. What does it mean? It means that in serial gray box models, the black box model and white box model follow one another, meaning that information from one and other model follow one another. And in parallel gray box models, we have the opposite. White box model and black box model operate at the same time, and their output is combined, and then we put that output in gray box modeling. To give you a better understanding of these models, here are some examples of studies where is used serial approach and parallel approach. Both of these studies have been conducted in the latest years. First one is done by Kreningfeld in this year, 2025, and the author and his co-authors did a research for 4 hybrid models on real building data. They used Energy Plus as a software for this simulation, and the results show that residual serial hybrid model gave really good results with really high accuracy, while surrogate models showed lowest accuracy. As for parallel approach, we have research that was done by Siever and his co-authors in 2023, and he did a gray box model with combination of artificial neural network corrector, and he wanted also to explore prediction of a temperature, but he used tree-zone building in this process and achieved high accuracy with experimental measurements while preserving physical interpretability. One of the most common models in HVAC and R system for simulating actually building demands in this kind of system is RC model. What means RC? R stands for heat transfer paths, and C are the elements that represent heat storage of the buildings or HVAC and R components. We will also have example of these kind of researches. And in the latest years, the focus of many studies has been on reducing these kind of models, mainly because of computational efficiency. And on the right part of the slide, you can see one proposition that was done by Reinders in 2023 that is shown reduced order RC model that showed really good result and often is used actually in researches later in 2024 and 2025. Okay, here are two really good examples of these RC models. First one is a research paper that was performed in Dubai for a building in Dubai under extreme weather conditions, and the researchers wanted to predict indoor temperature under extreme conditions. They used 6R2C model for that, and the results, you can see the results on the graph. Red line represents the predicted indoor temperature, and blue line are measured data. Green line is actually the absolute error that happened, and you can see that the results are really good. It's really accurate simulation. And interesting conclusion is that when they included building cladding, the maximum error was reduced from 5 to 1 degree Celsius, which is a lot. And second research paper that we found really interesting is a research paper that was performed on near zero energy building. And this is more complex research because it, can I go back now somehow? Okay, thank you. Yes, it was a complex research because it compared not only gray box and white box results, but also they did comparison for different calibration period of parameters for 1 week and for 3 weeks. And what they have discovered, with a more calibration period for 3 weeks, the results were better, but not too much better. They showed good accuracy, but as expected, white box model gave better results by 1.5% in comparison to gray box model. But maybe the most important conclusion from this research paper is that automatic calibration in combination with gray box modeling reduces human time by 90%, which says to us that it's really useful to use automatic calibration in these kind of simulations. As you can see, the gray box modeling can be really, implementation of gray box modeling can be really wide, mainly because they can predict dynamical behavior of the buildings, and often they are combined with model predictive controls. And now we will discuss 3 more research papers that actually that were also published in latest years. And for every one of them, there's a QR code. So if you want to know more and read more about it, you can scan this QR code. First one is done by Kim in 2023. And what was the objective of this paper? The objective was to conduct accurate and efficient HVAC and R simulation with automated parameter tuning. And they used a combined reduced order physical model with machine learning, so it's a combination. And as input, they used temperature and mass and volume rate. What was validated in this experiment? Pumps, heat exchangers, chilled water temperature, COP, and power. And what are the results? Results show really high predictive accuracy when in gray box modeling is combined with machine learning. And also the same conclusion as we had before, that calibration reduces manual effort by 90%. What is limitations in this research? Mainly because they used simplifications for the mass flow, and heat storage modeling gave some errors, but there's space for future work. Anyhow, the second research paper that we chose and found really interesting is actually from refrigeration systems. It was performed by Lierbeck in 2023. And he wanted to do a study where he would enable accurate fault diagnostics in refrigeration systems. In order to do so, he used nonlinear RC gray box model with nightly re-estimation of parameters, which means that he included system dynamics in his research. And the results were also really good. You can see on the graphs on the left side of the slide. He also concluded that this kind of approach can be used for larger scale applications. And the last research paper that we will discuss today is a research paper done by Mort in 2025, actually, and it's really interesting because they developed an efficient, accurate gray box model for building energy predictions in combination with model predictive control, and used 3R2C single zone model. Key features that are important to mention is that in this simulation, in this building they chose, they included thermal resistance, solar gains, infiltration, and air change rates. And with all of that, they successfully managed to, using gray box model, to predict energy consumption in cooling with an error of 2.0% and for heating with an error of 1.7%, which is really impressive. And only limitations in this work is because it's a single zone model, single zone simplification, and they were minor heat flows error. Here is just a short table with some research paper that has been conducted in the latest 2 decades that we found interesting. These papers were not mentioned in presentation, but we think it's important to see how much this area has been developing for almost 2 decades now, yes. And now we can go to the conclusions. Gray box models, as you saw, hopefully, provide really good predictions when they are used for predicting building energy demands. And mainly, the model that has been shown as the most accurate is RC models. They also support critical applications, and that is important for the future works as energy performance and system identification. Only limitations in gray box modeling are multi-zone interactions, modeling thermal inertia, and complex flow dynamics, which is also a space for future research. And here we put some ideas for the researchers in the future, what they can do. First of all, it's interesting to see what results will be shown if we implemented gray box model on a larger scale systems, multi-zone scale systems. Then it's important to develop user-friendly platform for maybe industry to use in the future, and integrate that kind of platform with AA-assisted technologies. And in the end, we can include gray box modeling in the earlier stages of building design. Thank you for your attention. If you have any questions, I'm here to answer. If not, you can email the authors, and here is the references that we used in this presentation.
For your presentation. Is there any question from the audience? Okay, if there's not, I have one.
I'm listening.
Because you said the gray box model is a combination of black box and white box.
Yes.
So we know that black box we include the experimental data. So in that we usually have deviations on different sides: air side, refrigerant side, water side.
Yes, okay.
So how this deviation go to the gray box? It's, of course, the deviation grows. How to overcome that deviation?
When the model is defined, it's based partially on equations. In those kind of equations, we can put parameters that can change over time. So if we know some parameter can really influence the process which we are modeling, we can put it in equation and then combine experimental data that has been, I don't know, for maybe last 2 years that has been measured and put it of importance in white box model. And in that way, while writing a script, we can control what parameters are important for us in our modeling process.
Thank you very much.
Thank you, Professor.
Further question. That's all. Thank you. So our final presentation is presentation performance analysis of regenerative ORC for the use of the waste heat from steam boiler. Nurdin Čikajić is maybe right. Da li možda Nurdin Čikajić tu? Jasmin Fezić.
Ja nemam ni jednu prezentaciju.
Dobro. Okay. That's all. And the last presentation, the author Livia Drohan, Technical University of Civil Engineering, Bucharest, Romania, apologized because he couldn't come. So I believe I should conclude this session. So thank you all for attending. Is there any question now for when you heard all the presentation? We have 4 different presentations, so very interesting topics. So is there any questions? Additional? If there's not, please one more applause for all the presenters. And that's all for this session today. Thank you very much for your attention.